So welcome everybody. Thanks for joining us for today's webinar on predictive risk assessment and groundwater contamination. I'll be your host or moderator. I'm Stephen Mamet. I'm the Director of Science here at Lyora by EMS. And I'm sure it needs no introduction. Our CEO, another Steve. I actually met a Steve yesterday at the playground. It feels like they're starting to multiply. Dr. Steve Siciliano, the CEO and co-founder, will be taking you through this journey today. So it'll be, I don't know, about a 40-minute presentation or so with some time for questions. We'll have the chat open, so if something comes to mind while you're watching the presentation, you can put questions in there. So with that, I'll hand it off to Steve.
No problem. Thanks a lot, Steve. And just as usual, we're always open to questions. These presentations, what we try to do is not to get too technical, but me and Steve are always happy to respond to technical questions and kind of do deep dives if people have questions about specific capabilities or maybe what we see as some challenges or what are some of the big benefits, all those sorts of things. We're always happy to talk about. For those of you who don't know, these sensors really came about from about 10 years. Well, I've been doing remediation since about 92. And then about 15 years ago, one of the larger oil and gas companies called Federated Co-op here in Western Canada, they're Western Canada's largest fuel supplier, approached our research team at the university to try to develop technologies that would really help them accelerate site closure and accelerate site decision making. And this technology is part of what's growing out from that. And so we're always interested in people's ideas and suggestions and questions, because I do think that this sort of technology and this use of the software and the hardware is going to really transform how we manage sites. And we're going to talk a little bit about that today. So we're going to really talk about how using predictive risk assessment and groundwater contamination can really help you in some of your decision-making processes. There's myself here on the left, and the other Steve Mamet. We'll be talking with you today. Of course, me and Steve, I think, have worked together for about 10 years. We were trying to figure out how many it is. It's over a decade now. And one of the things that we share, and I think everybody here shares on the call, is this recognition that we're all stewards of the land that we're currently on. And everyone on this call is really devoted to continuing on the historic traditions of caring for our land and supporting sustainable economic activity in both the renewable and non-renewable resource sectors. And I just want to acknowledge that we recognize that we're part of a long tradition of various groups and stakeholders that are really focused on supporting the land so that 7 generations from now, the land continues to support a vibrant human community that is continuing to improve the lives for their children and other people. So what's our mission? Well, to be clear, our mission at Lyora is to restore, repair, and improve the world's soils. That's really what we're focused on. A big part of a soil's function is cleaning groundwater. And without soil, you can't actually have clean groundwater. And so as part of that mission, we really focus on understanding the groundwater and what the risk is associated with that, because you can back calculate from that and make decisions on soil management that will lead to future predictions in groundwater. I will say that from a contaminated soils point of view, a key thing to remember is that groundwater is a lagging indicator of both risk and success. If you're successfully managing your site, your groundwater is the last thing to respond. And if there's a risk at your site, the groundwater is unfortunately sometimes the first thing, but as you reduce that risk, there's going to be a lag. Normally, the rule of thumb is you're going to have to reduce your hydrocarbon impacts by around 95% before you're going to start to see substantial ground and sustained groundwater mitigation. So let's talk about point-in-time sampling. So this is what our current industry standard is. We do high-quality sampling of groundwater, typically with low-flow sampling, where we're going to get a strong estimate of what the current hydrocarbon concentrations are in that groundwater well. So there's a couple reasons why there's some downfalls with PIT that are well known. And it's basically what is the traditional way of doing this. And with the sensors and hardwares that Lyora uses, we're changing that. So the first thing is that if we think about it, even if you're sampling your groundwater up to 4 times a year, effectively you're only sampling about 4 cups of water, so 1 liter, and you're only getting one point in time sample. And those point in time samples can vary dramatically due to typically if there was rainfall, if there's a current event, how well equipment is working on site. Although I would say that that's actually not as big of normally, in my experience, most field crews are pretty great, and most consulting groups are really careful to make sure they collect high quality data and have a good data quality program. But at the end of the day, we're making very large area results. We're inferring from a very large area from really at one point in time in a relatively small area. So one of the things that happens is the contamination in groundwater in particular is going to vary day to day for a whole range of reasons. We have pressure influences changing basically what our hydrostatic field is doing, in other words, what our groundwater table is doing. We have rainfall, temperature, and sampling technique. I would say most people use low flow, so that's less of the concern, but we do see this variability. And then manual sampling. It just takes a long time. One well, as a reminder, can take between 1 and 3 hours to sample if you're doing low flow sampling. And that means you're paying somebody for 3 hours to watch water come into a tube. And so the question is there better ways of doing this because it becomes very expensive to do this? And so how I kind of think about this is, sorry, having a little trouble. When you're collecting your data today, so for example, it's the springtime here. I know groundwater crews are starting to head out now. Samples are going to probably start to be taken over the next 2 months or so. And realistically, people are trying to make those decisions as to what they should do this year. But it's not really current. And that's the issue. It's very difficult to get the information in time to talk about what you're going to do during this year's season. And so that can really result in this weird time lag where effectively you're managing your site by looking in the rear view mirror. And so one of the key things that we want to really focus on is we want to visualize what matters. Like, why do we measure groundwater? And what are the key points? You have to know when your plume is stable. For some of you, your plume is stable. For other of you, you're still concerned about stabilization. And then for more recent spills, you want to understand what the risks are before they escalate, because if you can get in front of a risk early, you're going to reduce the amount of engineering time and cost it's going to take to mitigate that risk. So intervening early and smartly can really reduce those long terms. And unfortunately, sometimes what happens is because with the point in time samples, we're looking in that back view mirror, by the time we're stuck in a position of trying to mitigate the risks, our costs have escalated significantly for us. Either the plume has gotten bigger or it's created a situation where things like engineering controls are not going to be effective, or if they're going to be effective, they're going to be they're always effective. It's a question of how much time and money you want to put into it. And this also allows you, if you're collecting a lot of data, to understand and focus your budget on the high priority sites. And those high priority sites can be linked to issues related to liability mitigation. It can be linked to issues linked to remediation, but realistically, it provides you to move your decisions from a reactive to a proactive. The other thing about sensors is it really reduces field visits, delays, and I don't want to say unnecessary delineation, but sometimes you get a false positive. So for those of you who work on complex sites, such as a refinery or a midstream facility where health and safety is a very high concern, and there's a lot of people deployed every time someone goes on site, that can really help increase your operational efficiency. And for those of you who operate more remote, smaller sites, it really can increase your health and safety as well as your planning, because you're not putting people on the road to go visit these sites, and those people aren't necessarily working under adverse conditions where they're putting themselves or you, well, I guess more your reputation at risks. And so that is one of the advantages of using sensor-based technologies and softwares. So what's kind of the key thing? What is the plume risk intelligence? What can you really do with in situ sensors that are more difficult? You can do these point in time, but it's more difficult. So you can really predict your plume movement size and stability using historical data. We can upload historical data and give you a really quick estimate of where your plume is moving and what its overall movement rate is going to be over the next 50 years. And then you can use LiORA-based sensors to really help that. You can then prioritize sites with the highest risk of offsite contamination. So in some ways, I think that contaminated site officers are a little bit like general practitioners. 90% of your sites really might not be a really high priority. And you're really trying to catch those 10% that are high priority that maybe you don't realize they're high priority because your data is spotty and it's not clear that the plume is moving, which would be uh, which you'd want to get in front of. And so by doing this, you're allowed to prioritize your entire portfolio and say, here's where I want to put our budget this year. And to be able to do that effectively and evidence-based so that you can maximize the effect of whatever that remediation spend is or future delineation. And really, that's all about deciding faster, being able to make decisions really quickly on the site and decisions that are, I mean, for people who are managing sites, it's a very difficult situation because you always don't have as much data as you want, and you have to make decisions moving forward. And then I would view contaminated sites as a complex system. So a complicated system is a system you can plan out and you can understand it. And you can say, oh, if A equals B equals C. Something about a car is a complicated system, but we can engineer it so we're pretty comfortable that it's going to start and it's going to drive down the road in the way we want. Complex systems, by their very nature, and soil, contaminated soil, and soil itself is of the nature of the complex system where you have technically nonlinear responses to certain events, and so what happens is it can become very difficult to predict what's going to happen with great certainty. And so contaminated site officers are often stuck in a situation where they don't have a lot of data on a highly complex site. So they try something and they're pretty comfortable this is the right decision, but it's hard for them to validate that it is the right decision. And effectively, these where these sensors came on. I know one of the people on the call today, Jay, he and I were working at a contaminated site where we had tried something innovative, and it took us years to evaluate if that was really working or while using traditional samplers. And these sensors and this software has really helped to see, did the MP work? Did the ISCO work? Are these intervention techniques working? Or should I even worry about this site? Or can I just leave this site be? So what does a sensor look like? So this is what a LIORA sensor looks like. The key part here is you have this gas permeable membrane that lets gases in and keeps water out. And so that membrane is the new membrane, which is launching this year. We call it the Titan membrane. It's able to handle 100 psi of head, so it can go to at least 400 feet. I don't know why you'd want to put it 400 feet below groundwater, but it can handle high pressure. It has an anti-fouling component, and the most important thing is it's got very high solvent capabilities. In other words, it won't get degraded by aggressive solvents. I'm still not going to say you should put in an ISCO well. I don't think that's a good idea when you're injecting ISCO. Take the sensor out for that. Yeah, I should do that. And then the other key thing with the Titan upgrade is that the new Titan upgrade is going to allow us to have improved durability over multiple seasons. And we're very excited about by this upgrade. We spent a lot of time working with our partners over the last couple of years, identifying why sensors were working, where they were working, where they weren't. And the new Titan upgrade is going to do that a lot. There's still the gas permeable membrane. And how this works is any groundwater is going to have dissolved gases in it. And those vapors, or those gases, sorry to be technical, they'll actually equilibrate into the sensor body. And as they equilibrate into the sensor body and into our detectors that sit there, what happens is we then detect them using a type of detector called non-dispersive infrared detectors. And that then has automated data communication back to our servers. Now, I just want to mention about non-dispersive infrared is one of the reasons we picked that sensor technology is it's incredibly robust. It's used both in downhole drilling rigs as well as in flue stacks. And so it's a very robust technology, hermetically sealed emitters that allow you to put these sensors into very dangerous situations without concerns. And then that sensor then communicates every 30 minutes back to LIORA versus LoRa via LoRaWAN and Amazon Web Services. And so let's just talk about why we picked that. So one of the reasons why we picked the LoRaWAN and Amazon Web Services is really about data security and privacy. And we're going to spend some time today talking about that because I do think people should be thinking about, as we put more and more IoT sensors in, how can I ensure that my data is safe and secure? And one of the things that I want to really highlight is we often see this. And so I just want to I'm just going to ask Steve a question about this is that, when because we look at a lot of people's historical data. And so one of the things we often see about between sampling events is this variability that maybe a pollutant's gone up or gone down. And I know when Steve's trying to manage plume stability, this is a problem. And so, Steve, do you want to maybe describe to me, sir, what do you see when you're looking at what plumes are doing over the 4 or 5 years we've been tracking them? How variable is it like between seasons and things like that?
Yeah, it can. There's definitely a strong seasonality component, like with, and I suspect primarily related to water table, goes up and down. It changes that smear zone, and then the easiest thing to do, you want to use a non-parametric approach like the Kendall, which is basically just a regression on ranks to see differences, and it's a mixed bag. The approach, it makes sense. It's easy to implement most stats packages like Excel. You can do it in there very easily, but we do see a lot of seasonal variability, and that's one thing that you won't pick up on if you're using that approach. So
And
it's
does
it's tough with just a handful of sampling points to really make robust inferences about what's going on at a site.
And is there any way to use the man Kendall like with point in time sampling to deal with seasonal variability? Like, is there any way you can say, oh, I'm not going to use those site? I know my numbers are always higher after precipitation. Is there any way that you can robustly do that, do you think?
Well, my off the top of my head, I would think that you could subsample your data. You visualize it, and our brains are great at picking up patterns. Better than most computers. And so we can see right away. Okay, maybe if I exclude this, but then it becomes very subjective, and then you're not sure if how robust is this approach. If I've eliminated these points and then I've run this test, if Fred next door does the same test, is he going to get the same results?
And I think that's one of the big powers of with LiORA sensors because they'll collect 17,000 measurements in a year. And so it becomes much more convincing about what the trend actually is. And how much
Mhm.
would you say, how much groundwater variability do you see? Like not thinking about point in times, but just LiORA sensors. Like when you think about all the sites we're into and with the site with the sensors, with the groundwater, how much do you see strong like seasonality and sort of variability within a site?
Yeah, definitely. So often with just a year of data, you'll see that seasonality, and then you wonder if, okay, writ large, what is the trend? It's often you need that second year because you've got a lot of this going on. Because oh, go ahead, Steve.
Well, I was just wondering how big is this? Like, is this plus or minus 3% or plus or minus 30%? Like, what's your so for the record, Steve Mamet looks at every report you've ever gotten from LIR and all of the data, and we collect 500,000 data points a month. So we're not going to get into precise numbers because Lord knows Steve could give you that. But I'm just wondering, is it, plus or minus 3%, plus or minus 30, plus or minus 300%? Like where on average would you say?
I'd say it's in the tens to hundreds of percents.
Okay, even some sites at 100%.
Yeah,
Yeah. Okay. Well, that's something to know then. So, your risk can change quite a bit between your sampling events. And when you go back and sample, you're not going to recognize is that just this natural variability or not. All right. So how does this actually work? Thanks, Steve. So people always ask us this, and I think it's a really good question. So this is how effectively this works. So down here, the sensors, they'll drop into an existing groundwater well. And what's going to happen here is that you have down here, you have your slotted screen. You're going to have your basically your stabilizers. Your groundwater sampler is going to be right here. This is the LiORA sensor. It then has a hanging cable as well as communication that goes to this. This we call our top communication module. Now this fits snugly into the groundwater well. In this picture, just for clarity, it's shown being outside, but it'll actually seal into your groundwater tubes so that water coming over the top cannot enter your groundwater. This can fit in a flush mount. and so that it'll basically seal on the top. And then in this top part, what'll happen here, this is where your communication module is, as well as where your top communication sensors are. And then when people want to, if you want to go out and sample it, all you'll do is you'll just pull this out, snake up the cable, do your low flow, put it back in. I will note that typically we typically give our sensors about 4 weeks, 4 to 6 weeks to stabilize between insertions, to be sure that our data is is valid. Is what I would say, because what's happening here is when you pull it out, of course, it starts to equilibrate with the atmosphere. We don't know how long it's out for, and then it goes back in and it has to equilibrate. Now, once it's equilibrated, it'll respond pretty quickly. So, Steve, I have another question for you that someone was just asking me yesterday. He said, well, if it takes you 4 to 6 weeks to equilibrate down hole, then how confident, like, does that mean like a groundwater change is going to take 6 weeks to show up the sensor? And I know you've looked at this of day by day variations of a sensor that's in the same well. And so how would you respond to that? The question is, do these sensors only change after something's changed in the groundwater for 4 weeks?
Yeah, the thought, I'm not a physicist, but the analogy that just came to mind was static versus kinetic friction, that it takes a long time. It's harder to move something from stopped than it is to keep it moving or to change it. So I think the same analogy would apply to our sensors here, that, because in the next webinar, you might see me wearing glasses because I spend so much time doing this, staring at data on the screen. But yeah, it's usually, depending on the metric, you see this relatively steep slope in the data over time, and then gradually it stabilizes. And then you see these finer order fluctuations that can be, tied to the environment rather than just equilibration. So it takes a while for it to stabilize, but once it's stabilized, then it's more sensitive to the environment.
Yeah, how I think of it rather than friction is I think about it as sources and sinks. And at some point, after it's equilibrated, after that 4 weeks or so, that sensor pack is basically the difference between that and the groundwater should be almost nil. So any change in the groundwater is a relatively small change inside the groundwater sensor housing, so it can respond quickly. Whereas when you first put it in, it's a huge difference, and it just takes a while to actually get up there. So, thanks. That's one of the key questions we often get. And so after, the next stage is, what does the data look like? And this is the part that one of the reasons that I really want to highlight here. So we have our sensors on the left side, and what'll happen is they're going to transmit to a LoRaWAN gateway, and that LoRaWAN gateway will communicate back to can communicate many ways. It can be plugged into normal internet. It can go through cell. And then what happens is when, in essence, how we think about our sensor takes a reading, and it takes that reading and it puts it into an envelope, and it says, here's these numbers. But what's happened is before that sensor has left our building, it's given an encryption key. We're the only one that holds that key. And so the sensor automatically encrypts it and then bundles it in an envelope. The envelope gets sent to that network gateway. And the only thing that network gateway knows, sensor one at 12:30 p.m. on April 15th, here's the envelope. Where does that need to go? Oh, that needs to go to EMS. It's fully encrypted. Even if someone opens the envelope, hacks the gateway, they still aren't going to be able to understand what's happening at the sensor, because it's heavily both compressed and encrypted. I mean, we're typically only moving about 32 bytes of information, so it's really compressed. And then what happens is it hits the gateway, and the very first thing that happens is it hits our servers through AWS typically, or the Things network. And what'll happen there is we'll decrypt it and we'll decode it. So we're like, oh, this is sensor 5 that was present here. Here's its code. Here's its encryption key. We add those two, and then we explode out the data. Now we have all the data. It then goes into our database. We store that raw. We then also convert that raw. We calculate what that means in terms of pollution levels, and then we push it to the front end. And so we've got this database in the back where we keep that raw signal all the time. We keep the data that's been processed by it all the time, and then we then push that to the front end. So how does the actual PlumeFutures work? Well, we have the initial information. often historical data or your legacy data. And from that, we're going to make a model. We're going to make a model using ModFlow, pretty standard USGS agreed upon sort of groundwater model. And what we're going to do then is we're going to create this initial groundwater model. And then what's going to happen is we're going to get this incoming data from our sensors, which is then going to update the model, and then the whole thing gets updated every month or so. So initially we start with your legacy data, and that's the very first thing you'll see. So you'll see that under PlumeFutures. You'll get to see how your plume is moving and what our forecasts are. And those are based on average values for that area in terms of conductivity. Any information you don't have, we have basically set defaults that we use based off either CCME guidance or depending where our US guidance. And then what's going to happen is as data comes in, we're going to start to update those defaults. And that gives us a lot of improved confidence in the outcomes because the initial model, it's pretty good, but then what we do is we use the data to make it great. And so a good example here is if we were looking at a contaminated site. So this is a real world, it's not a contaminated site because this is actually where LIORA's headquarters are, where our production facility is. We have not contaminated for the record, but what we've got here is we've overlain a real plume. And what we can see here is what we call our baseline. So this is what effectively it's going to be moving. The light blue is the existing groundwater field, and you can see how we normally predict about 20 years. And then what the lines are in yellow is your potable water guideline. What the orange is the vapor inhalation guideline, and the red is the threat to aquatic life. So those are basically what those numbers are, is they're set to specific concentrations that are informed by the regulatory criteria. Then the next one you can take a look at, this is NSD. So this is incorporating what the natural depletion is, because a normal groundwater model does not incorporate natural depletion. So here we have what our natural depletion is that can be informed by our soil sensors. And then we have been working in biostim for a long time. I think we're working across 25 sites. And on average, what we then do is say, well, here's what we know what will happen to depletion when you do that. And you can see here that this results in a much longer a much smaller plume, ideally going to 0 in 20 years. And so what this allows you to do, and you'll get this in PlumeFutures, this allows you to say, well, what am I okay with? I mean, in terms of, am I okay with just the baseline? I'm fine with that impact off site. Or I'm like, oh, I can do NSD and just nothing will leave my baseline. I'm happy with that. Or maybe I don't want that. Maybe this is still too high. I'm going to want to get rid of it entirely. Then what we can ask you is we can do our biostim. And then if you decide to do other remediation, that's fine. We can incorporate those predictions as well. Now, the real value of the continuous data I think of is, here's an example of an actual plume. And what happened here on the left side is this is the initial model. So we have this initial model here, and I just want to highlight this is a well where our sensor was. And the initial model was pretty comfortable with the groundwater model. You can see down here at the lower left and the right that you know, it's pretty stable down here. The model's very comfortable. It has some uncertainty here, but if you're looking at it, say, oh no, we're pretty good there. And then what happens is that as we go through this data simulation, often called data fusion, there's a whole bunch of different names. If you want, we have a whole technical webinar on the actual math involved here. But what you can see is that as our sensor is updating, our uncertainty is actually increasing, which sounds counterintuitive. But what's happening here is the sensor data is telling you something that you don't know. There's something happening at this site that the sensor data is suggesting to you there's an unknown here. And if I was to see this on an actual site, I'd say, hey, I think you should probably put another groundwater well here. Because one of the things, I mean, we should all, realistically, almost none of us work on undisturbed sites. All the sites are heavily disturbed, historical impacts, historical activities. And so these groundwater models make assumptions that you have this uniform field. Well, that's a little bit of I'm overstating that. But the idea is the groundwater models don't account for things like, well, maybe there's an old buried UST there, or maybe there's an old utilidor there. It can't account for that. And when the sensors come in, they're like, oh, in this particular case, right up here, it's saying, look, the model's not hitting convergence. And that's where you can bring in other knowledge or decide to go take more samples and be much more comfortable with where your estimates are. Okay, so why use PlumeFutures? Well, it really does allow you to look at sort of your triage. So, a good example here is on the left side. We have a site that actually is looking pretty good. Within 10 years, it's going to move well, actually. Um, a time to fence line on one of these sites is going to be about 10 years is going to be moving off property. And you can see in this particular case that time to plume stability is about 46 years. That's really bad news. This is a site you should probably be working on. This site is going to expand for the next 50 years, so it's worthwhile to take a look at. Now, this is all theoretical, but then that allows you to say, okay, well, what can I do now at a relatively low cost and not too intrusive to actually mitigate this long-term risk, rather than waiting for 10 years to now go, oh my God, it's off-site, we got a legal claim, et cetera, et cetera. So let's take a look at what it actually costs. So if we take a look at sort of annual sampling, at a large site, you're going to be looking at around 200K. And in contrast, layer is going to run you about 400K. Normally, it's going to take you about 10 to 12 years to be comfortable with your plume stability. We can normally tell you within 6 months how stable your plume is. Now, of course, there's seasonal fluctuations. So normally what we'll tell you is say, look, the plume's looking pretty stable. You're probably going to have to monitor for a year or two to be sure, just to be sure that there's seasonal variability. Normally, we'll do one trip per year to do the install. And depending on the type of install the type of things you're happening, you might have to change batteries, or if you elect for solar, you definitely don't have to go back. The biggest question, the biggest thing here is that you've got 17,000 data points per year compared to 2 to 4 points per year. And this is what me and Steve were talking about with that Mann-Kendall test. The reason people use the Mann-Kendall test is it's really well suited when you only have 2 to 4 points per year. That's what it means when we talk about non-parametric and rank ordering regression. They're really good at these levels when you have low data, but they make massive trade-offs in terms of their power to detect changes of any sort. Now, when we think about the plume stability, we've already talked about sort of the amount of analytical variability we see. And I just want to highlight that because me and Steve were taking a look at that when you're looking at your plume stability. So here's a complicated graph that I'm going to let Steve Mamet explain because he made this and I can tell you about it, but I think he'll do a better job on it. It's based off a lot of data. So Steve, do you want to walk people through this?
Yeah, so some feedback that we've gotten on our own sensor data is that it's highly variable, and uh, often we compare things to, say, this is groundwater sampling data, which is sort of treated as the gold standard. I thought, well, we've got a pretty good database of groundwater sample data. Let's look at sites that have been sampled at least twice in a season, and then see how much, and this is benzene, how much it varies over the course of a season. And when we actually looked at it, we found that almost half, samples taken sometimes only a month apart, you can have a doubling or a halving of benzene concentrations. And then even so, fold changes, a twofold change is a doubling, just for reference. So in some cases, we had several orders of magnitude difference when you look at the right-hand side of this graph, the very right-hand yellow box there. So even within a season with the gold standard of characterizing these sites, you can see a lot of variability. Whether that's real or not, we're not sure. But it does highlight the need that, well, if just 2 points, you can have such a difference between them, and that might not necessarily be real. You might want to have a little bit of a finer sampling, a little bit more data to see what's going on at a site, even just within a season.
Yeah, and so Steve, one of the things I know people have asked us about is, well, I'm not too surprised at this because all these ones that are varying a lot must be very low concentrations, like 0.0005 milligrams per liter benzene point versus 0.01. So in thinking about, you're the one that looked at all the raw data here. Do you think all of these are just super low concentrations, or are some of these like, oh, it's 5 milligrams per liter benzene?
Yeah, off the top of my head, one comparison I recall, the benzene was 6 milligrams per liter, and then a month later it had doubled to 12 milligrams per liter.
Yeah. Yeah, and so that's one of the reasons why these sensors came from, because I saw the same thing with soil sampling, right? Like we'd go, we'd drill, be good, and we'd go back and we'd put a borehole right beside it, and our numbers would be completely different. And one of the advantages of the way our sensors work is you can imagine they're integrating signal. So you have your groundwater, and effectively it's diffusing across. And so you're getting this integrated signal. And then we take a snapshot in 30 minutes. And we take another. That's why we collect every 30 minutes. The reason we collect every 30 minutes is it really allows us to integrate this signal over time. So that way, when we see this variability, and I think, Steve, you said that when you're thinking about a site, you often see the groundwater varying by about 10 to 20% within the year. Is that right?
Yeah, yeah, that's probably the average. There's definitely some higher variability, but that's a good
Yeah.
average.
Yeah, and so by integrating it, we get rid of these extreme values of like 10 is 10x. So in that previous case, it would be, going from 1 milligram per liter to 10 milligrams per liter. And so we're able to really moderate that. That's why we collect so many samples. Whereas if we just did a groundwater sample twice a year, even with our sensors, it would still be a problem. So that's one of the huge advantages of us taking 17,000 samples versus twice a year. Okay, thanks, Steve. So, I think today we sort of highlighted some of the questions about being able to prove plume stability relatively quickly and make decisions. You can always book a call with myself or Carolyn. We can talk through that. You can also, if you're not ready for sensors, that isn't a problem. With our PlumeFutures can work off legacy data, off historical data, and you can send that. All you really need for that is either PDF reports or um, or Excel sheets. And what we do is we then initialize that model, and you can get very quickly, like within 3 weeks, you can get yourself a snapshot of what your groundwater is looking like over the next 20 years, and that'll help you prioritize your sites.